Welcome back to PV Online. Today we're going to look at the difference between weight and mass. Very often we interchange them because we're always looking at the surface of the Earth. But if all of a sudden you were going to go up to the moon, or if you were going to go into the space station, you would need to know the difference between them. Now all mass is the amount of matter. How much stuff is present? It has a unit of a kilogram. So the unit for mass is a kilogram. Weight, on the other hand, depends on where you are. If I were to stand on a bathroom scale here, let's say I weighed 130 pounds. If I were to take that same scale and go up into the moon, I would weigh about 25 pounds. So since weight is a force, it has a unit of a newton. So weight and mass are not the same. Weight depends on where you are, mass doesn't. So let's take a look at a couple calculations. We've got Felicia, our ballet dancer, has a mass of 45 kilograms. So her mass is 45 kilograms. So if we wanted to find Felicia's weight on Earth, we know that her weight equals her mass times the acceleration due to gravity. Now, as far as symbols, as far as equations, you might see this sometimes, that the weight equals the force due to gravity. Those mean that they mean the same exact thing, that I could over here write this, that the force due to gravity, which is by definition what weight is, equals mg, or that weight equals mg. They both mean the same thing, so don't worry about it. Either one of those, they all represent the same thing. So we want to know the weight on Earth. Well, I'm looking for weight, which is a force. The mass of my ballet dancer is 45. What is the acceleration due to gravity on Earth? It is 10 meters per second squared. Now, I don't worry about the negative sign because I'll know when I do force diagrams that the weight is acting down. So all I have to do is multiply those two numbers, and that gives me 450. And since it's a force, that means the unit is a newton. Now for part B, we want to find out what is Felicia's mass on Jupiter. All right, so now we're taking her to a different planet where the acceleration due to gravity is a lot larger than the acceleration due to gravity on Earth. We want to know what her mass is. Now remember, her mass is independent on where she is, so how much matter there is still 45 kilograms. The mass is the same no matter where she's at. But let's take a look at, for part C, what is her weight on Jupiter? So using that the weight equals the mass times gravity, I'm going to take her mass, which is 45, times gravity, which in this case is the gravity on Jupiter, which is 25 meters per second squared. And I multiply these two numbers, and I get 1,125 newtons. Does this mean her clothes don't fit anymore? No, it just means that the force of gravity pulling down on her on Jupiter is much larger than it is here on Earth. How your clothes fits relates much more to your mass. All right, so let's take a look at this. We have an astronaut who weighs 858 newtons on Earth. And we know that weight equals the mass times gravity. Well, if I know the weight on Earth, I need to use gravity on Earth. So it says, how much would he weigh on Jupiter? So he's going to weigh a different amount. Oh, he's going to weigh a lot more on Jupiter than he did on Earth. So the way to find this is let's find the mass, because I know the mass is going to be the same both here and on Earth. So the weight is 858. I'm going to find the mass because that doesn't change. On Earth, the acceleration is 10 meters per second squared. Let's solve for mass. And I'm going to divide both sides by 10. And when I do so, I get 85.8, and the unit for mass is kilograms. So now I'm going to go back and use my weight equation, weight equals mg, but I'm not going to use 10 meters per second squared this time. What am I going to use? Well, I'm going to use 25 meters per second squared. So I put in my mass, which hasn't changed, and I'm going to multiply that by 25. The weight then equals 2,145 newtons. So our astronaut weighed 858 newtons on Earth, but now all of a sudden his weight jumped up. Again, the mass didn't change. All right, we'll see you next time.